Mic check, mic check. 1, 2, 2. Mic check, mic check. 1, 2, 3. Mic check. Excellent. And do you guys have any audio component in your presentation?
Check 1, 2.
Here's a handheld as well, in case you don't want to like kind of stand at the podium. But it's just like a quick flip up.
Check 1, 2.
Thank you.
Yeah, no problem.
Thanks. Yes. Yep. Yeah, absolutely. You're very supported. Yeah, yeah. I was like, I don't want to cut their time short, so I think we're 1 minute early. But by the time I finish, we should be good. So thank you all for joining us. Very excited today to have Shannon and Aarya share what they have done at their institutions. And so just as a very brief introduction, there's more about them in the app. But Shannon Rhoads is at UNC Chapel Hill, and she's an image analyst at the UNC Bioinformatics and Analytics Research Collaborative, which we commonly refer to as BARC. And Aarya is joining us from the Microscopy and Histopathology Collaborative Laboratory, or CoLab, at Seattle Children's Research Institute. So very excited to hear about what they've been doing to educate their users and really promote image analysis workflows at their institutions. And then just wanted to make a quick plug for the light microscopy research group for those of you who are light microscopy related. There are multiple sessions, one this afternoon at 4:30 and one tomorrow at 10:45 that are LMRG specific. And if you want to learn any more about that, go ahead and ask Erica or any of us. And also just a quick plug for Bioimaging North America. There's a poster number 45 that's up, and Heather Brown is around, and we have some stickers. If anybody's interested in stickers, come find me. And very finally, for global bioimaging, if you go to your homepage in the app, there is a current survey just on what are the main challenges that people in core facilities are facing these days. So please take that. And for those of you who are light imaging related, if you click on the Global Bioimaging Authorship and Acknowledgement Survey, that is specifically for people who are imaging and trying to get a global perspective on how we can increase authorship and acknowledgement. But without further ado, want to hand it over to Shannon.
Okay. All right. It's great to be here today. Thanks for attending our session. I, as Michelle said, am an image analyst at UNC. And I just want to share a little bit about kind of how I've been integrating image analysis into our university as a relatively new aspect of the core facilities. And so I've titled my talk today, How to Teach That Image Analysis is Not One Size Fits All, because I feel like that's a really common kind of assumption that people come into when they start new projects. So main takeaways for my talk today, I hope that you are able to take away what researchers need to understand to be successful image analysts. Some benefits and drawbacks of two different learning approaches that I have recently implemented over the past year to try to teach these strategies to researchers. And then a brief little guide on how to pick the right software as it really kind of guides the whole image analysis process. Okay, so starting with important things to know for successful image analysis. The image analysis process generally. So starting as early as sample preparation, you prepare your sample, you take it to the microscope, you take some images, collect some data, you sit down at the computer where you do quantitative analysis, and then you answer cool questions. A lot of people come in and think that this linear process is what they're going to be experiencing when they start the image analysis process. That is not at all true. At any point in the process, you need to loop back to any earlier part in the process. So your sample preparation, you may actually be adjusting that all the way through to the point of determining your analysis approach. Same thing with the microscopy settings. And even when you just are happy with your sample prep, happy with your microscopy, you may need to sit down and iterate on the actual analysis approaches that you're choosing. Even I can't suggest to a client right away, you should probably do these steps. Maybe I'll be right, maybe I'll be wrong. They still have to sit down and kind of iterate through that process based on their unique data. So big picture here, the image analysis process is iterative. The next aspect is that images are really complex numerical data. So when we look at an image kind of zoomed really far in, we see that it is just an array of numbers. And these numbers have lots of components. So yes, they kind of all represent, in fluorescence microscopy especially, how much stuff, how much light was collected from our sample. But thinking about it in terms of what do we care about, every channel in our image has different components, like our signal of interest, the background, so maybe the stuff we don't care about as much, and then on top of that, noise. And all of these things can be impacted by any number of choices that we make in the imaging and analysis process that can impact how we choose our analytical methods downstream. So when I'm sitting down with clients, it's pretty often that I hear, is my image good? Or if they've gotten to the analysis approach already, is my analysis approach good? And these are important questions, but I like to frame them more as, is my image good enough to answer my science question? Is my analysis approach good enough to answer my science question? So how do we determine what good enough is? Every single image analysis scenario is different, as I just alluded to with the number of choices that you have to make along the process, so that every good enough is also different based on your images, but also based on the question you're asking. So just to give you a very specific but relatively simple example of this, counting objects. We care about that a lot. But lots of things go into how can we count objects, how effectively can we do that. So your choice of microscope, for example, can impact things like resolution of your images. Resolution can then impact your ability to identify and count objects. So if we are imaging nuclei, for example, we have this high resolution example of nuclei imaging, as well as a lower resolution example of nuclei imaging. From both of these, you can collect the same data if you are simply just trying to count the number of nuclei there. But if we have a different goal, if we're trying to identify and count different objects like mitochondria, which are quite small compared to the nuclei, the same high resolution setting is not going to be the answer. You probably are going to need a little bit higher resolution than here. The low resolution is definitely not going to be your answer. So all of these small choices along the way are going to impact your ability to do quantitative analysis and the choices that you have to make when you're deciding how will I approach my quantitative analysis. So how do we make these informed choices? How do I go into something and think, I'm going to choose this microscope over that microscope, this analysis approach over that analysis approach? I think fundamentally, it's understanding the actual image analysis methods themselves. So for somebody who's just beginning in image analysis, what is an image? It's an array of numbers, not just a pretty picture that I can interpret with my eyes. Secondly, mathematically, what are all the things that I'm doing to my image actually doing to my image? So if I apply a filter or a certain manipulation, how does that impact the numbers that I'm getting? Because ultimately that will impact my quantitative outcomes. And then lastly, how do we use the values in the image to actually derive information or meaning about biology? So for example, we can use intensity values to tell us things like where objects are, so object segmentation, or measure intensity of objects, so how much stuff do I have? What is the relationship of that stuff? So to summarize, big picture, what researchers need to understand going into image analysis processes to be successful is that image analysis is not a one-size-fits-all thing, because there are so many choices. It requires iteration at every step. There are many choices that have to be made that impact many different things along the way. You have to have an understanding of fundamental image analysis methods to make good choices. So this is all, maybe if you are in image analysis or you've done this a lot, maybe seems really obvious, but to somebody starting out or somebody that's getting into a more complicated project, this isn't always easy. So the next thing I want to kind of switch gears to talk about is how can we teach this to researchers? So these are, I'm going to share just a little bit about two of my experiences over the past 2 years in a workshop environment and a short course environment where I tried to teach kind of the similar material. The first environment was an immersive workshop where we focused on introducing image analysis through ImageJ, so a graphical user interface-based analysis software, open source, and Python. But the Python had no coding requirements. You didn't have to come in knowing how to write scripts or anything like that, just introducing tools to people kind of at baseline to get them toe in the water, familiar with what's going on. Then a graduate level short course where they focused on learning 2 different GUI-based analysis softwares, ImageJ and Cell Profiler, with an emphasis on automating repetitive tasks that they would be doing in their image analysis. They had similar amounts of time to learn these topics, 12 hours in the immersive workshop, 15 hours in the short course. The immersive workshop, however, was 2 sessions, so 2 days in a row, 6 hours each. And then the graduate level course was 10 sessions of an hour and a half each. The population for the immersive course, it was anybody at UNC. Any researcher at UNC could apply, but we had lots of people applying, limited number of spaces, so we did have inclusion criteria for who we ended up selecting. For the graduate level course, anybody who could attend a graduate level course could attend. So there was no selection criteria. This ultimately led to lots of graduate students, some postdocs, some staff. In terms of the style, the workshop was very demonstration heavy, and students got application of how to apply the methods we're learning through those demonstrations. And then in the short course, it was very theory heavy, and the only application they got was independently, so through homework or like in-class independent work. The formatting, just to go in a little bit more detail here, because I think this is quite important. The workshop focused mostly on how to build pipelines, how to make choices to build effective pipelines. The graduate level course tried to cover a diverse amount of topics. We have diverse researchers that join our course. So we covered lots of different things, hopefully hitting some topic for everybody. In the immersive workshop, our outline for what we were teaching started with what's an image, how do we assess image quality, and then built on top of that as we went. So how can we derive information from intensity values? What if that doesn't work? How do we pre-process? How do we post-process? Then how do we consider, what do we consider when we build reproducible pipelines? What do we consider when we think about statistics? Big picture, what does the analysis process look like when we're starting a new project? And all of this was done with one continuous data set. So they were very familiar with the data set. In the other course, we covered similar topics. What's an image, intensity values, thresholding, different pre and post processing steps, and then a ton of other options. So we covered lots of things hoping to hit everybody. But with these diverse topics came lots of diverse data sets as well. So at this point, I hope that you're thinking there's lots of benefit in each of these, maybe some drawbacks in each of these as well. For example, exposure to different data in one, good knowledge of the data in the other. So what were the outcomes of these 2 learning environments? I will say, just to be very transparent, that I did not have the same survey for both. So I will only be comparing the responses or the questions that were similar between the 2. Those were mostly free response questions. So I've tried to synthesize down kind of the most meaningful things from those 2. So immersive workshop, 95% response rate. Short course, about 72% response rate. Still great for both. In terms of positive feedback for the workshop, the most common thing was that people felt like what they learned was relevant to their research. I said this in many different ways, but essentially this is what it boiled down to, which was nice that they could identify, I can use this in my research. Then some comments about it was nice to learn about reproducible pipelines, how to justify my answers. The demonstrations were great. In the short course, we had kind of our top answers also about reproducible pipeline building. They liked that a lot. Use of Fiji macros. But then otherwise it was kind of a smattering of, well, I like this, I like that. Somebody else liked this other thing. Lots of different outcomes. In terms of constructive feedback, for the workshop, what was most confusing or difficult was actually the demonstrations. People felt like once they got lost, there was no coming back from that in a lot of cases, even though they seemed to be positively received in most scenarios. Otherwise, there was kind of a little bit of here and there on what other people didn't like. In terms of the short course, for improvement, they really wanted demonstrations. So I get it. The other thing that they wanted different was the homework assignments and the class structure, mostly centered around needing or feeling like they needed more guidance in how to get started in their homework assignments. So kind of centering around this idea of like, show me what to do at least a little bit so I can get started. And then otherwise there was, you know, diverse opinions on other things that needed to be improved. So, okay, boiling this down, the workshop seemed to be more applicable to the selected participants despite covering less topics. The short course had a little bit of something for most people, but there was also lots of comments about this was really good, but this was not very good, and it was quite diverse. Hard to kind of narrow down what we might remove or add. For the workshop, they seemed to really appreciate an emphasis on creating pipelines, making choices, how to justify those choices, but they did want more tools to do so. So we didn't cover things like Fiji macros because we were going right into Python scripting, but they wanted kind of the in-between as well. For the short course, they valued the tools for pipeline building, but didn't quite know how to put the steps together or justify how they did that. The workshop demonstrations were occasionally challenging to follow, and the short course, they really wanted more demonstrations, more guidance on how to get started. So, all in all, I think a combination of these two approaches is going to be the most optimal scenario. For the short course, I probably will bring in more things about decision making. I don't know that I'll give them more demonstrations, but maybe a couple more videos on how to get started. For the workshop, I think we'll cover a bit more tools along the way. But one open question for both is which group actually integrated more useful information that will positively impact their research? I don't have the answer for this just yet, but I am teaching both of these again in the coming year. So I do hope to reassess past cohorts, future cohorts, and try to have a more kind of continuous survey for both. Okay, so moving into the next section, and kind of the last part that I haven't talked about so far is software. Software can kind of guide your whole image analysis experience, especially when you're working with a client and you're not choosing the software yourself. So making those smart choices to help your users pick the right software is important. So this is kind of a little guide or easy way to start thinking about choosing the right software. First, what software does the required task? So to be specific, use a specific example, segmentation of 3D objects, which can be challenging. Here you see a three-dimensional neuron in culture with a fluorescently labeled Golgi and mitochondria. If we wanted to segment those things, how do we do so? What's the best software? Things to consider. The required computation. So here, three-dimensional segmentation. There are several softwares that do that, including ImageJ, Cell Profiler. Python does a great job at that. Amaris does a good job at that. But things like QPath, probably not where you want to go. Next is the type and amount of data that you're needing to process. So if you have a lot of data, batch processing might be something that's quite important to you. Different softwares do different amounts of batch processing. Some are easier, some are harder. You might also consider how big your images are, what kind of computational power you need to have. I think Aarya is going to talk a lot about that, so I'm not going to touch on it right now. Another thing is open source versus proprietary. So I'm a huge proponent of open science, so moving towards open source software if you can is a great choice, but sometimes that is a limitation. You have what you need in a proprietary software that your institution has purchased. So for these, Amaris is not open source, but the others are. So for this particular task, I might narrow down the software choices to these 3, for example. But there's more to consider, especially when working with clients. So how easy is the software to use or learn? What is the average learning curve of that software? So something to consider related to this is, are there graphical user interfaces or not? Fiji and Amaris both have great graphical user interfaces that have good documentation, so you can probably make your way through with relative ease. But Python obviously does not, and you have to learn a whole new coding language if this is not what you do every day. But when you're working with somebody else, the skill level of the researcher and the researcher's goals is something that you have to keep in mind. So if they code in Python every day, that's an easy, okay, great, we'll keep it in the mix and allow the researcher maybe to choose. If the researcher's goal is to learn Python, then, and they want to use this as the opportunity to do so, maybe that's the approach you take. Otherwise, maybe stick with ImageJ or Amaris. Okay, so that's just a quick snippet, just something to keep in mind. It's very important, guides lots of what you end up doing. To summarize all of this all together, image analysis is not a one-size-fits-all process. To teach researchers this concept, they need to understand basic principles of image analysis methods. They require iteration. There's many choices that influence the images as well as the analysis process. Images are really complex numerical data, and you have to understand what the method is actually doing to understand how you can utilize that in your quantitative analysis. Second, there's different styles of teaching that can be used to teach these things to new researchers. Demonstrations can be quite helpful, but also, maybe they don't quite teach the user to be independent right away. But I think overall what I've taken away from both of my experiences this past year is that an emphasis on decision making is maybe the most important aspect of this, because you're not always going to be there to help guide them. And then the last thing, choosing the right software is quite important. Lots of things to consider there, but it will kind of make the biggest impact on the analysis process. So with that, I'll say thank you. This is my contact information. I'm also in the app if you're interested in chatting with me. And I'll be presenting in the statistics session tomorrow, the other LMRG session. So thank you.
We're going to move on to the next one, and then we can do questions for both of them at the end.
Okay. Hi, everyone. As Michelle earlier introduced, I'm from Seattle Children's Research Institute. I lead the microscopy core there. Our core is less than 3 years old, so relatively new compared to most of your cores out there. And whatever I'm sharing today are some of our efforts within this short time frame and the lessons we learned from that. And as Shannon just demonstrated, we heard a lot about the how and why of image analysis, which are very critical for scientific rigor. But once a researcher has perfected their Python script or that cell profiler pipeline, they often hit a wall, the desktop. So I want to tell you some of our efforts on how we have tried to scale our analysis beyond the desktop. Within our core itself, we have seen how microscopy data has exploded, both in terms of volume and complexity. And I'm not just talking about an increase in the number of images we acquire. We have also seen how these images evolve from 2D snapshots to 3D volumetric images to 4D time lapses, 5D channel multiplexing images too. And here is a list of the instruments that we have currently in the core. We have 3 confocals, and all of them have a super resolution module on them. And whether it's Aarya Scan or Sora, what we have seen is the images that come out of the system, they have larger bit depths, they have smaller pixel size. So we are not just dealing with bigger files, But these files also often need some form of deconvolution or like a intense post-processing workflow before the actual scientific analysis can begin. And one more instrument that I want to highlight here is our SmartSpim light sheet from Life Canvas Technologies. So the average raw data that comes out of this instrument is in a scale of terabytes. It's not a few gigabytes anymore. And this terabyte is very easily acquired in less than 3 hours. So that is one high-resolution image of a whole mouse brain in just 3 channels. So acquisition is not the slowest part of our pipeline anymore. But when you think about analyzing a terabyte-sized file, that is not a matter of hours. It could be days or maybe even weeks. So that calls for an infrastructure which is scalable, which is reliable in terms of data security, and also gives us a compute environment that is reproducible every time we try to do that. And that's where the HPC solution comes in. So HPC, or high performance computing, it is not one giant supercomputer. It is a cluster of computers that are working together and are connected by a fast interconnect. And it is this architecture that will help us push beyond the limitation of a standalone workstation. And what this means for our researchers is we can deal with those terabyte-sized files at a much faster pace. And we are not just doing bigger data, we are also accelerating everything from like AI segmentation to 3D complex registration. And this would give them faster turnaround. And more importantly for us as a core, we are able to come up with an automated reproducible workflow, which can then be shared with diverse groups. So we're trying to move away from like one-off task on a local machine to something which is more shareable and scalable that can be used by several users. Now this comparison is just to show you the raw power of our HPC. So the HPC at Seattle Children's has been named Sasquatch because we are a children's hospital, we get to come up with cool names. And here are some specs of the 2 local workstations that we have in the core. And even the Lightsheet workstation, the IT team told me that this is one of the most powerful workstations that we have in the Institute. It is a really beefy PC. It has a very good Threadripper 24-core CPU, really good RAM, a very nice graphics card, but when you're dealing with terabyte-sized files, you often come to a limitation there as well. And if you look at the specs on the Sasquatch, you can see how much the scaling factor is. When it comes to CPU power alone, it's more than 250 times powerful, 145 times more memory on our Sasquatch, and 80 times more GPU space. And more importantly, it also has a 20 times faster transfer of data between the different computer nodes. It also has more capacity, obviously, but on HPC currently, this storage is only temporary. It's only for the data that is going to be analyzed on the HPC. We have a completely different server where the data lives long term. But other than the storage, you can see, I hope you can appreciate the raw, the power of Sasquatch compared to our local workstations. Now that you have seen this comparison, the next logical question would be, can I do my analysis on the Sasquatch? And like any other microscopy question, the answer to that also is, it depends. So it depends on the workflow that you're doing, because there are some workflows which are suitable for HPC, and there are some that are not so suitable as well. So one of the great examples could be a workflow that has a high degree of parallelism. For example, if you're thinking of a high content screen using multiple 384 well plates, you're going to have several images from that one screen. If you think of each of those images can be small, but you can parallelize the kind of post-processing or the analysis that is required. So that's easily scalable. It's a lot of data volume, and it can be computationally intensive if you're trying to do everything on a local one machine. But this is something that you can put on an HPC and then distribute the workload. And our HPC, like I think most other HPCs out there also, is Linux native. So if you do have an open source software or anything which is Linux native, that is also compatible with the HPC. So some of the examples include ImageJ, Cell Profiler, Napari, Scikit, and any deep learning algorithms that may be there. At the same time, there are also some workloads which are not so suitable, something that requires a sequential workflow where you have to wait for one data to be processed and analyzed to start with the next one. So there, you are not really using the full potential of HPC. That can be done on a standalone workstation. Something where the data volume is very small, so just the process of having to move your data from one server to HPC and back and forth could slow down your pipeline. Something which requires a lot of interaction between you as the researcher or the user and then the application, because HPC is like a headless system. You're going to do everything through a command line interface. So something that requires interaction is not compatible with HPC. And then the main thing is also, because it's a Linux native system, anything which is Windows or Mac native applications are also not currently portable with our HPC. And sadly, that includes most of our microscopy-based applications. And that, like some of the ones that we have in the core, Zen, Arivis, Imaris, NIS elements, sadly, none of these are compatible with the HPC. And what does the HPC workflow look like? So at Seattle Children's, if you are a new user to HPC, we first request an account so you can access this resource. And there is an orientation and training provided by our HPC team to onboard you to this. And once this is done, you start by logging into one of these two login nodes. So these are, whenever I say nodes, you can think of it as a computer within that cluster. So these two login nodes, they are fully functional nodes, but we don't run any actual task on them. So this is just used as like a landing or a launching pad. And from there, you have access to two directories. One is a home directory, which basically, that's where you'll store your login files, any configuration files, any password required, any particular environment required for your Python script, any particular R file installations. So all this is stored in the home directory. And then you also have an association directory. That is where you'll be storing your actual data, which is going to be processed and analyzed on the HPC. And on our HPC, this is given in an increment of 1 terabyte space. So for our microscopy core, we do have an association directory. It currently has a 5 terabyte space, but with our light sheet, we're actually going to increase it to at least 20 terabyte, so we can deal with multiple light sheet files. And once you've connected to HPC, the first step is going to be transferring our data, which is going to live on our RSS, which is the research storage server. So that's where our data lives long-term, and the data has to be moved from our RSS to the HPC for analysis, and this is not a queued job. And once the data is there, we're going to use a scheduler called Slurm to actually schedule the jobs. And this is where we are going to tell, okay, how many resources do we need? How many CPU cores do we need? How many GPU we need? What kind of memory we need? And for how long? And it's the scheduler that makes an efficient choice about, okay, what resources are available and what resources do you need, and then kind of designate and dispatch or execute that job. So similar to, let's say, if you were to walk into a restaurant and you have a wait line. And then depending on when the table gets available and depending on how big your party is, the hostess is going to seat you. So it's an exactly similar concept, and that's what the scheduler does. And once your job gets dispatched, it's get executed, the output is going to be written to a directory that you have already specified within your association directory. And once that is done, then you can move your data back into the RSS. So this is sort of like the simplified workflow that we have currently on our Seattle Children's HPC. And I want to talk about two use cases where we have actually used HPC for some of the microscopy data. One of them is for a confocal data, and this is going back to a high content imaging, which was done by one of the researchers, and they were imaging several 384 well plates. It was a large screen of more than 800 mutants. And they were taking 10 ROIs per well, and all of those images were a multi-channel Z-stack, and in some cases there were some time series also. So if you think about each image, it's not that big, but just the volume of images that were being collected, that's like several thousands of images, and they had a repetitive pipeline to follow for each and individual images. So that included masking, applying a filter, segmentation, and quantification of multiple parameters. And if they were to do it on an individual workstation, I don't know how long this could have taken, but this was ideal for a containerized batch analysis on our HPC system. And at the bottom of the slide, I've shared 2 QR codes. So the first one here on the left, that is the original pipeline that was developed. So it uses some off-the-shelf image analysis tools to do automatic segmentation for the cell and also for one of the subcellular organelles called peroxisomes. So the entire pipeline, they called it perox per cell. And this is something that they have validated against manual counting as well. And this can also be used for other subcellular puncta-like structures, but you may need to tune the parameters accordingly. So the way the pipeline has been developed, it expects the input to be a multi-channel Z-stack to have at least 2 channels. One to mark your cell boundary, so you can do the cell segmentation, and then one to mark your subcellular structure, so you can do the segmentation for that. And your output is actually going to be an Excel sheet, which all of those parameters that you have asked for to quantify. And there is a publication from that pipeline. And then the QR code on the right is a modification of the same pipeline. Here, they've also done a nuclear segmentation in addition to the cell segmentation and then the subcellular structure segmentation. And the publication will take you to the actual scientific paper which has used this publication. And just by deploying this on HPC, just to give you an idea about what was the scale, they were able to segment 1.3 million cells each day on the HPC. And this was a big screen, and they were running it on the HPC for like 6 months. Now, imagine if you were to do it on a standalone workstation. I can't even think how long that would have taken. So this is one such example. And then another example that we are currently working on is to do some of this light sheet image processing. So for each light sheet image, the raw image has some streaks that need to be removed post-acquisition, and that's called destriping. And most of the light sheet images, they are multi-tiled, so you need to stitch them together before you do any segmentation or registration and analysis. So what we started doing was we identified the common workflows which are going to be usable for all our users. So that include the destriping and stitching. So currently what we have is a GUI version of these on our local light sheet analysis workstation. But what we are also doing is these are based on some open source softwares. So for destriping, it uses an algorithm called PyStripe. The stitching software is based on TerraStitcher. Both of these are available on GitHub. Both are open source. So we are using the command line interface version of these softwares to deploy on the HPC. And at the same time, we also came across this pipeline, which was developed by Allen Institute of Neural Dynamics. So they are our neighbors, and they're just like across the street. So it was also very easy for us to collaborate with them. So, and the good thing is they have the exact same microscope that we have. So we thought, okay, that might be easy because they've already customized it for this particular instrument. That might be easy for us to just follow the same thing. But the first roadblock we hit was, for some reason, their input directory is very different from our input directory, even though it's the same instrument. So we had to change a few things there. But I think we are close enough to do our first deployment. We're planning to do it either later this week when I get back to Seattle or maybe next week. So we are going to start with a smaller data set, a 20 gigabyte file, just to see how the whole pipeline goes without any errors. And then after that, the plan is to scale it and try it on actual terabyte size light sheet files. And I also wanted to briefly show you how the data workflow in our microscopy core looks like, and also where HPC comes in this pipeline. So for most of our instruments, from the acquisition BC, our data gets directly transferred to our RSS, which is the research storage server. And we have an active storage tier and then an archive storage tier. The active one is called Helens, which is named after Mount Helens, which is an active volcano. And then the archive one is Baker, dormant volcano. So any data on RSS can be accessed from any other children's device. So it can be easily accessed from any of our post-processing or analysis PC that we have locally on premises. What we've also done is enabled a direct processing with a 10 gig network connection. So for some of the instrument, as and when you are acquiring a new image, they can do the post-processing parallelly. So that removes some of the bottleneck. Now for HPC, all the data gets transferred from RSS to HPC for any scalable analysis, and then it goes back to RSS once that is completed. And this is the workflow that we have for most of our instruments. And for Lightsheet, we do have a few extra steps because of the scale of data we are dealing with there. So even for Lightsheet, yes, we do have a direct processing, and the post-processing PC has the GUI versions of our destriping and stitching software. And what we also introduced here was to have a short-term data storage on premises. And that has a faster connection, a 25 gig connection to both our post-processing and then our analysis PC. So any data that you're actively working on with the local machine, you can have a faster access from this than if you were to try and access it from our RSS server. And for long term, it goes into RSS, and we're also exploring a cloud storage option. Now for HPC, for the pilot project we are doing, directly after acquisition, the data goes into our RSS, and from RSS, it goes to HPC and then back once it's done. Or the other option could also be, you can do all the post-processing locally and then move the data to RSS and move it to HPC just for the analysis part and then back. So this has been some effort which has been going for the last, I would say, 6 to 8 months or so, and there has been some integration challenges. One of them has been the data transfer bottleneck between our RSS and HPC, because so our RSS server is in Tukwila, which is about 10 miles south of Seattle, and our HPC is in San Jose. So every time we have to move the data between these two, there has been a bottleneck there. But our IT team is also looking into maybe building a new computing cluster closer to Tukwila, at least to deal with these bigger data sets. And then the second integration challenge has been workflow compatibility. As you know, most of our microscopy users, they're more used to the Windows-only or a GUI-based version. So to completely go into a Linux world and with a command line interface, there has been a big gap there. Again, like with limited coding experience, it has been very hard to push the users to build something on their own and optimize any pipelines. But in spite of that, I think we've still made some progress, definitely including a direct processing line, whether with a 10 gig line, 10 gig network connection, or the 25 gig for the Lightsheet. That has helped us remove some of the bottleneck. And then we have also started launching specialized image analysis workshops, similar to what Shannon said. I think in the previous years, we focused a lot more on ImageJ, Fiji, Imaris, but this year onwards, we've actually started focusing on Python scripts as well, just to help lower that barrier to entry, to introduce people into this new system so that they can scale their analysis on the HPC. And we're also working very closely with our HPC team to identify some common pipelines as pilot projects so that can be used by several of our users, so they won't be scared about command line interface anymore. A few lessons learned. I do feel core, we are in a unique position to actually bridge the gap between our researchers on one side and then the IT. And whatever progress that we have made was a true partnership between the core and then our IT team. And we do have like a monthly regular meeting with members of our research IT and then our scientific computing to talk about where are the bottlenecks, where are the challenges, and what can we do to make this whole experience better for our researchers. And it has been helpful to have a basic common pipeline as an actionable start, so we have something to work on together. And then the last thing that I also want to mention are some commercial alternatives to custom HPC. Now, full disclosure, we don't have either of these computing clusters in our core, but we do have their standalone licenses on our local workstation for both Nikon and IS Elements, and then we have a partial license for Erivis as well. But I was also thinking about maybe there's some of you in this room here who don't have access to custom HPC, or because of some of those integration challenges that I talked about, where you really need a Windows-only application or a GUI interface. Maybe these are some alternatives that you can think about. So Nikon, it's basically, if you have used any Nikon instrument, if you have used the Nikon Elements, they also have a server license where you can actually have on-premises Windows cluster. So for example, the 2 workstations that I mentioned that we have, we can use them as 2 nodes. And I just have to get a server license for the NIS elements that we currently have, maybe have an additional seat. So the way this is going to work is the server license is going to offload the processing, just like a regular HPC. So like how we have our custom Seattle Children's Linux-based HPC, this could be an alternative if you're thinking about like offloading Windows-based applications. And one thing I liked about this was also they have enabled a zero-click workflow. So there is a watch folder, and as soon as an acquisition is ended, it can actually automatically trigger your deconvolution or your post-processing or your analysis workflows. And they've also integrated with this with some of their AI modules. And the Zeiss Arivis Hub, this I've heard from users that the Arivis software can actually handle terabyte-size files really well. And one thing I like about Arivis is it's format agnostic. So you don't need to have a data which was acquired on a Zeiss instrument specifically. It can be any other format also. And this can be run either locally on a server or on the cloud as well. So just something to think about if you're thinking about scaling your analysis pipelines. And with that, I come to the end of my talk, and I think we can open the room for questions. Thank you.
I don't know, is this on?
Yeah.
Okay. Thank you. Those are really interesting talks. I have kind of I guess it's like a administrative structure or practical question, particularly for the last talk. So if you're helping, I don't know how your core is organized or supported, but if you're helping an investigator design a pipeline or help them learn to get access to the high performance computing cluster, how do you predict or account for or support the staff time that goes into that?
Yeah, the HPC, currently the HPC team, they do provide trainings, and there's a lot of onboarding. They have a lot of tutorials to get people started on it. And the good thing is also there is no chargeback for using the HPC resources. So it would be actually the time that basically an HPC staff spends with them. So what we are trying to do is that whenever we do image consultations, we do try to address their most immediate image analysis needs and how they think about scaling this also. So if they are thinking about, okay, starting with an Imaris pipeline, but they know that, okay, in 3 months they would want to do this for like 500 images, we do think, like urge them or encourage them to think about, okay, maybe some other pathways to do about it. Yeah, did that answer your question?
But you don't have to charge for your time for that consultation? Like, is that covered by your institution?
So our core is, I think it's in a very unique position right now because it's a single person run core. It's just me. So my bandwidth has also been very limited when it comes to the amount of time that I can provide support. But that being said, actually in exactly 2 weeks, we do have a new scientist joining our institute, somebody with a machine learning background and AI. So we are looking forward to forming a little bit more close collaboration and consultation with each of these research groups.
I will just piggyback onto that. I do have some projects that are entering use in our HPC at UNC, and that is time that I charge. So I just charge my normal hourly rate. But similarly, we have an IT team that is available for like kind of the entry level, problems that might occur. So I don't have to necessarily troubleshoot that kind of thing.
Hi, I'm Kelsey. I'm with the UW Histology and Imaging Core. I think we're also neighbors. Might be a naive question in relation to your talks, but you brought up the fact that there's a lot of data being generated and server usage. I know our core is looking to maybe start like a fee structure for storing data on servers, and I was wondering if either of you have experience with that. We're kind of struggling with how to structure this, and I thought it might be a good question to ask this room. I'd love to piggyback ideas if anyone has experience with that, or if that's something that you're implementing or have implemented.
Yeah, so actually our research IT does charge each lab depending on how much data is being stored. So that's why they have those two tiers. There is active storage. So anything which is stored in that tier, you will have faster access to that data. So you end up paying more for that. And then for archive storage, the understanding is you don't have to access it that often. So then you pay a lower tier fee for that. So there is a chargeback to each PI. And I think, and that's something like we are working on evolving and modifying, because initially when this was set, I think 5 terabytes was given free for each PI. But now, as we see that like all this data, it's been exploding a lot, right? And 5 terabytes can be filled in like 3 hours, 4 hours. Yeah. So yeah, so we have been actually talking to IT about, okay, how can we expand that? Maybe 20 terabyte would be like a good starting point. And then I think what we don't have in place is also a good data policy regarding how long do you store the data. And I think when it comes to microscopy, whenever IT has asked me, so how long do you want to store this light sheet data? It's been unlimited. Like we don't have, yeah. So these are things like we are definitely thinking about. And I think when people have to pay for storage, I think they'll think closely on, okay, do I really need to store this data? Or can I put it like somewhere else?
Okay, thank you. Well, if anyone else has any ideas, feel free to find me after. Thanks.
Hi, great talk. So my question is, we have the same problem where if you really want to get to the nice command line tools, like the user experience, it's just so formidable for a lot of users. Like they really want to live in the GUI. And so are you aware of any tools that would let you like start to build like essentially a command line builder that you would start with the GUI interface, you have your Amaris or Fiji, and then like some way to translate user selected GUI settings into the command line that you would then run on the full data set, like in a streamlined way? Or is this still done ad hoc by someone who knows what they're doing?
Like the image day macro recorder, but
Yeah.
that would be great. I don't know of anything though.
Yeah, I'm not sure. Yeah, I don't know. Maybe I'm sorry. I'm putting David on the spotlight here, but I know Fiji has both a GUI as well as a headless interface, but I don't know how easy is it in translating one form to the other. Yeah.
I will say that our HPC does have a desktop, so we can utilize Fiji in the GUI format through our desktop. So I'm not sure how challenging that is to have your university or wherever you work set up, but I think that is kind of low-hanging fruit into at least getting people comfortable with the idea of going to a virtual machine.
Okay. Thank you.
Hello, I was just curious when we're talking about all this data moving back and forth between the HPC and the native computer, are we doing any file conversions out of native OME TIFF or other TIFF conversions to any of the other compressible / dividable file formats? ZAR is the one that pops up into my mind to be able to spread that data across the different computer components.
Currently, we haven't done any conversions, but that's the next thing on the Lightsheet pipeline that we have to do a OME ZAR conversion. But we haven't done that yet.
Okay. I was just curious if you had any experience, but it sounds like that's in the works. So.
I had a question about the image analysis classes or workshops that you put in. I'm working on building some of my own, and I sort of a question, and I guess specific question, a general question. Specific question is, for your demonstrations, did you just demonstrate it, or did you have them follow along?
Yeah, it was live demonstration, and they had access to the data, so the expectation was that they would follow along, which, as you're planning, takes about twice as long as you actually think
absolutely.
it does.
I've been, yes. Yeah, but I guess being part of those workshops, that having someone that walks around and helps to make sure everyone's staying up, it's just sort of helpful for the student to keep along and know what's going on. So I'm just curious about your experience with that. Then I guess the other question is sort of general of, do you have any more recommendations about setting it up? And mine would probably more on the workshop area, at least to start. So we need your recommendations for anyone setting this up, starting.
So I guess to address your first question, definitely having some sort of TA is very helpful, because I think a lot of just small issues were mitigated right away. I think it does depend on the learner a little bit, if their learning style is being met by these demonstrations. I found that the same people were kind of struggling through a lot of the time. So our TAs did have to spend more time with those people. Anyways, your second question, general advice, I don't know. I really think the biggest advantage that came out of the workshop that I taught was the order in which I shared information. So I think that, and I didn't go into too much detail, but starting with the foundation of like, how do we just measure an intensity? And how do we just use the intensity values to do a super basic threshold, and allow them to do, some interactive time with those basic principles. And I think setting that up first and then coming back to, okay, well, what if this doesn't work? Maybe we want to add a smoothing filter or a denoising filter or something. And then they're already like, oh yeah, that would have been really nice when we did it, earlier, as opposed to how you would actually implement a pipeline where it's filter first, then segment, then measure. I think that was the most helpful thing in getting them to kind of smoothly integrate all the information. Otherwise, yeah, I don't know. We can talk more if you have specific questions, but yeah, that would be my biggest advice.
Thank you.
Yeah.
Hi. I have a question about the cost. So, what was the cost of this HPC system, and was it like internal money, or you got it somehow via an external grant? Was it like institution money, or it must have been expensive? That's what I guess.
Yeah, so I think, I don't remember the full history. So this was, I know the effort of this started 10 years ago or so, when Linux was not even like an approved language at Seattle Children's. So it started by our former director of HPC getting that approved in the first place. And then I think we had a previous version of HPC called Cybertron. Then that got replaced by a separate one. So Sasquatch, I would say, is like the third in that generation, which is much more powerful than what they had. So I think there was definitely a lot of institutional support. I am not aware of any other external funding that has gone into the HPC building right now. Yeah.
And the price?
Sorry?
The price? Roughly
Currently,
the price?
how much the researchers pay? Or
No. The price to get all this together, how much it was, if you have an idea.
I have no idea. Yeah. But I can.
Yeah, and it's also the computational power which comes with it.
Yeah, but I can actually ask my HPC team and get back to you on that.
All right, I was just curious. Thank you.
I was scared to ask because then they might start charging us for using it. So, well,
Yeah, I was scared to ask you too, but thank you.
Hi, thank you. Great talk. So one question for Shannon. First, you mentioned like how the users will ask, is this image good or good enough? At that point, it's kind of late to be like, no, right? So, because like, no, take all those images back. And so how do you handle that? Because I know part of the onus of like getting the images analysis ready is on the facility, but also you train them and you leave them up to their devices. And then they bring you oversaturated images and they're like, oh, localize, like stuff like that. So how do you handle that on that level? Do you have them consult with you before they set up the experiment, or like do you communicate with the facility, and just kind of how does that work?
Yeah, a little bit of everything. If they can start in the very beginning, that's the best case scenario. If we can get ground floor, like they have pilot data and I can sit down and look at it with them and suggest ways that they can improve or change, that's the best
Does
option.
that happen often though?
Sometimes, yeah.
Okay.
Yeah. I mean, we even get PIs come in to, help with grants, and then that's kind of like we're already in the ground floor there. But other times, you're right, like they have a full data set and they're like, I need to analyze this, and there's no going back. I don't have these samples anymore, or whatever the case is. And I think the hardest part at that point is getting them to realize that there are now limitations. And I think even when there are options to go back to the microscope, getting people to understand that there are limitations is really challenging. Like it's not going to be perfect every time, and so we have to work in the realm that we're in right now. So I don't know, a recent consultation comes to mind where we were looking at these tubular structures, and she could see them. I was like, okay, maybe they're there, maybe they're not. I don't know. But you know, we can only see what the image is telling us. So these numbers are the only thing we have. So just kind of establishing that was quite challenging. And, you know, at that point, there's only so much we can do. So we tried some filters, we tried some denoising, we tried some deconvolution, and I think she ended up going with a deconvolution approach. She was wanting to be relatively independent with this, so I don't actually know where the project ended up from here, but it is hard. I mean, you know, you can only get so far once you're at that point.
Thank you. And my next question is for Aarya, because the light sheet data is such a complex issue. You get the raw data from the software, from the acquisition software, and then you merge them, you dial, you know, you mix the dials, you do what you need to do, and then you have an IMS file, but you don't really need the super raw data, which can probably sit in a cold storage. Do you have any, like, I don't know, flow in mind about that? How do your users do it? They just kind of take the raw data and they park it somewhere. They're not going to access it forever, and then just play with the IMS file, for example. Or do you have any thoughts about that?
Yeah. So I mean, so we've had the light sheet. We got it fully set up in October, so we've only had it for 5 to 6 months. But at least so far, what I've been trying to communicate is, so you have your raw file out of the instrument, and then you have your destriped files, and then you have your stitched file, and then the IMARIS file, right? For the most part, I don't think there is a reason why you would need your raw file before the destriping, because technically the first usable data is after the destriping. So what I tell them is, once you have destriped, we don't need to keep that part of the raw file. And then once the destriping is done, maybe there are, I do know people, sometimes they try to, they have different stitching algorithms that they would like to try. So that may be a reason why they want to keep the unstitched data in there. So that I do recommend keeping that, the unstitched data. And then the IMARIS file goes into our short-term data storage, which has direct access to our analysis PC with the IMARIS file in there.
I know this is a good discussion. We're not going to solve it now, but I think the raw data is because if you publish later and you need to put up your raw data even before destriping, because that's a processing that's so I don't know how that works. It's been discussions for a decade or more, so we're not going to solve it now, but I wanted to hear your thoughts.
Maybe that's a question for the next 4:30 session.
Yeah,
they're talking about light sheets.
So.
Oh, yeah.
That's a question for you. Yeah, do not answer it. Don't answer that question.
Yeah, okay. Thank you guys so much. If there's no more questions, I guess we'll end a bit early. Thank you.
Okay, yeah.
Well, maybe several hours.
Yeah. So for me, I think bottleneck would be something which is really slowing down you down, and I do feel like that shouldn't be the critical part in the pipeline, data transfer. If you have to wait an entire weekend long to get your data to a place where you want to analyze, and I'm like, oh my God, is that what is really slowing me down? Okay, yeah. Yeah, I think that's why, because it's on, yeah. So that is the difference. So we are in Seattle. Our server, the main server where all the data lives, is in Tukwila, which is Greater Seattle. 10 miles. okay, but HPC is in San Jose. So that is the bottleneck. So now I think we have gotten IT to think about maybe building a new cluster closer to where their server is, at least for these big data sets.
Absolutely. Absolutely, yeah. So I'm actually about to reteach this workshop, like next week. So I've been thinking a lot about this, and I think
so. Yeah, we are trying to get there.
after they've been in class for 5 years, you know, like after we've gone through demos all day long.
Are you okay? You are from okay, Baltimore. Okay.
To try to build that redundancy in their brains, but then I'm going faster to try to avoid that, like, you know, taking up so much time. And then I think people got lost. You know, we're like 10 clicks in, like, you haven't opened the image yet. So to combat that, I'm actually providing a demonstration sheet that it's going to be a little bit organic in the class, but I'm going to actually follow what I've written so that they can actually, if they get lost, it's
For
right
the
there. So that's my first approach to solve the challenge about demonstration.
And so we were thinking, so two reasons. So one, because of that data transfer bottleneck, I think our IT itself is actually considering maybe it might be worth having a smaller cluster closer to where the data lives, at least for these big data files. So we don't have to worry about moving it from Washington to California.
Go and learn.
Kind of thing.
This is where you
So that
find
is,
the manual
IT is just starting to think about it. So,
so
even if that
I really like
gets
that approach as
executed,
well,
I think the timeline is not anywhere going to be like the next few years. Yeah.
So you need to know how to find the information that you need to be able to trust that information. So
It's
I don't know,
debatable.
it's challenging. That's
Yeah,
why
I think
want to do
because I do know like our IT, our head of IT also wants, because we are part of the Children's Hospital, like he keeps reminding, okay, we are here for like the hospital thing. We don't want to be an IT company. So he is pro outsourcing things. But then I think sometimes they also realize it's going to be much cheaper if we just build it ourselves. So
like
I think it's all.
Yeah, so they all use the same data set.
Yeah.
At the end, you're going to build something else.
Yes. Yeah, so in the class, their homework was, here's a data set, here's the question, and then along the way answer like these series of things. So like, you know, add the filter, include a screenshot of, you know, what the two channels look like filters. And so like we can keep track of kind of what happens along the way. There's not, that class is
And
like
then the other commercial alternative that I mentioned in the end, like that was something that I don't know, I'm considering it, because one, then it will be a Windows-based
we're
cluster.
actually adding in a whole other day.
And then I'm thinking, so in like Nikon Element software can run on it. Maybe there are other Windows licenses too, which has a server option that can maybe run.
Think about making choices and how that might impact theirs.
Yeah, we have the floating license manager. So thinking about it, I mean, I did like, you know, kind of tell our IT about it. They were not super thrilled because they are like, why do you want to do that? Because we have our HPC kind of. But yeah. So I'm thinking about like using our existing hardwares to start with, and then but then we just have to pay extra for like their server license, extra seats for each license that we have. But thinking about it, like
Yes. Right.
Yeah, absolutely. Oh yeah, for sure. Yeah.
This is a product called Chithran that we've been playing with people that like amazing makeup products like this. But what's cool is the way it works. It was originally created for
Yeah.
And so what you do is you
Absolutely. Yeah.
through a workflow, like as a teacher, you push a screenshot of the step where the teacher has to do something, or like
Yeah. So that's why I think HPC storage is temporary. The long term, yeah. HPC is free, but the storage is temporary. Otherwise, people would just be storing there all the time.
And like when I say this is cheap, it's like doing collage art.
No, we don't want to. Oh my God, no. Yeah. I mean, as soon as I have a hard time getting people to clear the data of the acquisition workstation, so I don't want to go more into billing and other things.
So that's a problem. Information, you can have like photos pop up, which like explains the thing more depth. Or you can post video, or like break out, and so then
Yeah.
that there's like you can make
I'll just
long. You can do that like super thing. You can make this like easier. And you can like have it very
Yeah. Right. Yeah. 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 That's the expectation that I have set too. But I still feel like I do want to check with people before I delete anything. Yeah. But then at some point you are like, I just don't have time to email them and wait for a reply and then come back next week to do this. So yeah.
You just edit the whole thing and then you change the screenshots. So what is it called? It's called screen.
Yeah.
You've made a copy someplace else.
Yeah. Yeah.
Okay.
And I make it clear that if I have to do, like, if something goes wrong,
Actually, what I was thinking for the short course,
Yeah.
like when they don't get demonstrations, but they want them. Like, okay, let me just provide you with a little, 10-minute something or other.
there's
so that we don't have to add, 5 more hours to class time. That's awesome. Thank you so much for showing.
Just something to think about. Like, we have to learn different
Yeah.
you don't feel like waiting around for weeks.
Yeah, awesome. Thank you so much.
Yeah.
Let's pretend you want to set up a already. You want to set up a
Nice to meet both of you. Of course.
transfer stuff between your analysis. Or you find yourself able to basically say, this is the heart, this is the floor of data transfer that I need.
Yeah.
Thank you very much.
I think yes, we do have a really good partnership with our IT. So and by we, I do mean the entire shared research resources. So we do a monthly meeting with like, and all of our codes are pretty like same board, like within 2 to 3 years, and all the codes are single person run.
Yeah.
So we have a meeting where, so everybody has the same thing. So we do have like somebody leading the genomics course, somebody on the flow course. So it's all we're all learning and growing. So we do have a meeting with our IT, like somebody from HPC, somebody from research enterprise, somebody from the storage server, and we do have like very meaningful discussions.
Workshop where I
And
can
chances
see
are,
the
I mean, so we
screen of
have like
everybody.
data,
When I lose somebody, I can immediately say, here, click there, click there.
Right. Right.
So we,
At
and
some
I think
time
when
point, because all these workshops are a foundation built on each other.
Yes.
When you move them here, they're unable
They're
to follow.
gone.
Exactly.
I know.
one
So
thing that they, so that's another reason like why what I put there, like we
interesting
actually
that we have to do this like how many people you can watch? 10, 50, 20, that gets
Maybe.
So exactly. Then
Yeah.
so 10 and then there's
So
the
we
process.
need to,
But I
like, unlock some of
promise
it.
that
So,
the 10
touch wood,
hours,
it
the
has
10
been working so
you
far.
save time in the long run because otherwise you have to do 10 hour in
Right.
because they will
Again
come
and
to
again.
you and ask the same question.
Yes.
That's
Yeah.
like,
And I
it
know
sounds stupid at
we
the
don't have
beginning.
those layers
At the
because
long run, I promise that
So do you ever record any of your workshops? Okay, we weren't
because
either.
Normally, if you're starting something up,
I decided
Yeah,
against
so
this
I don't know why they chose, I don't know
interactive
what went into the
workflow. That's
Yeah.
the question
So
that
this was
asks
all
a lot.
like,
Because when you do a thing about just
so I don't know why
like YouTube, when somebody gets stuck
why
at
not
the time point,
somebody
they have the
watched
same
it,
argumentation.
Yeah.
Everything after this falls apart.
Yeah.
You have to catch everybody and their needs and
maybe something
doing.
regarding
Yeah.
like how much it costs to
Another thing is,
Yes.
I do see you asking about the surveys, right?
Yeah.
I don't know what they do. Just for an example,
For sure.
I do the FFTs and the Fourier transformations, right? And I said, how do you like this? The fun fact is, everything I can discuss, this stays in. Everybody hates the FFTs. Everybody hates.
Yeah.
2 years later, everybody loves it.
Oh.
This is the only thing they say, oh, this is the one they remember, and it's useful now because I understand this with the ring FFTs
me too.
and whatever these newer techniques that come out,
Yeah,
how
I
this
think
works.
Yeah.
So the answer is, they don't know what they know.
Yeah.
You
I
pick,
know.
you pick what they have and bury the case and look, I know you hate this, trust me,
It
it's
will be
worth
fine.
knowing.
Yeah. Okay, that's a good way to think about it.
Man, it's like I know that you don't understand this,
Right.
but that's not the point.
Right.
The point is that you get the concept and say, there was something at one time. And the other thing is, I showed the repetitive task at the beginning.
Yes.
There's a repetitive process.
Yeah.
I learned the lesson that this is even one further, that this is not statistics.
Oh, yes, I know.
Because often the question we get is how many images.
Yes.
And the answer is you have to go to the statistics to see statistics, the significance. Then I can tell you every then we can pick the instrument. Because maybe the difference is on the confocal 5%.
Yeah.
But when you need 5,000 images, that's useless. Maybe the distance is only 1% of the wide field, or because you get 10 times more images, go with the wide field.
Yeah, it's actually a super good point.
You have to go the full way.
Yes.
Because when it comes out, okay, the imaging is working, the analyzer is working, but the difference is so small that I need to 1 million images.
I know.
And then you say, but why do you say confocal? I'm like, I didn't know what.
We didn't know. Yes, it's a great point. So I'm actually talking about, I was recently doing lots of reading about this, and I'm tomorrow presenting on an approach to calculate the number of cells that you need based on sample data, like pilot data sets, to do very basic statistical analysis. Yes, so you need a pilot data set. So you need just as much as you would need to do sample.
If you have exponential, if you have a power law, if you have an exponential, they change the numbers, and you need at least that you know what distribution it is.
Right,
I don't trust users that they can judge what you know.
No, yeah, it's like using pilot data set, so you know your standard deviation and you know your effect size. Generally, obviously, pilot data is pilot data, but you can at least get closer. So, anyways, that's what we're talking about tomorrow. Yeah, I didn't include it in here, but it's a great point. I should, because it's really like one of the biggest deciders, honestly.
And this is decision from my boss and me, that we don't comment this. We do the image statistics, and this is where we draw the line.
On the decision.
Yeah, on the
after
decision
that.
stuff, because we're getting in huge trouble when we say significant and not and blah blah blah.
Yeah.
And say no, I'm not doing this.
Yeah. Give you the number.
Exactly. My job is to extract numbers out of the images.
Yeah.
Give you an advice. Blah blah blah. But the fundamental stuff is a statistics course.
Yeah.
And the fun fact is, they charge 10 times more than we do. Because they don't have instruments that subsidize it.
Yeah.
So
Me either.
Yeah, exactly. But they come and do that. Do you know what they charge? I know.
I know.
And now you value me.
So funny. Okay, wait, question for you though. How many people do you actually get that come to you and say, can you do the analysis for me and give me the table?
No, this is a no.
Almost no.
This is a no. No, they come to me. I tried this at the first 2 years, and this gets out of hand.
Okay, so you just say no.
So so rough number would be I make pipeline for 200 people a year. I can't do this when I do this for each to the end. So the stuff is, you come to me saying what you want, I develop a recipe, and then I teach you on the recipe. And then we can change all the way how to do this. But at the first moment, like, let's make it simple. We talk an hour, I play an hour, I kill you an hour. Within the hour of my salary, you get your first number.
Yeah.
And that's what the price is. We bought it, and I bring this up in the first 10 minutes of when somebody comes here. So this is an agreement that it costs you at least one number, $120 to get your first number.
Yeah.
When that's not what your PI wants, because he thinks you are for free, Google, or then come to me. So I don't mind when they are very motivated and Google, and then come to me and ask for advice.
Yes.
And then I say, okay, listen, this makes sense, especially now in the world of ChatGPT. If I can Google stuff, and then I say, okay, I would do this or that. You can sell this. You know what this is doing? No, okay, that's not that. But as a fun fact is, they learn more. The price is the same.
Yeah.
Because the explanation is the one-to-one where you do normally the work classes.
Yeah.
Because they're the same sense. This is my. I include more the second way a lot of different examples. Where I say, okay, listen, what is filtering doing? And the first thing, okay, you can Gauss filter. What is Gauss doing?
Right.
Yeah, you trade in resolution versus equal to noise.
Yeah. Basically.
It's like you image your stuff with the worst objective.
Yeah.
Question is, I should not allow to do this because you image your stuff as the resolution you want. The reason I'm allowing to do this you picked the wrong objective.
Right. Because we have to.
Because you image in the 60x, you need a 20x. So the first thing I do, I make out your 60x and 20x, and everybody is happy.
I just had a STED project come in, and I was like, "Are you sure you guys want this?" And I was like doing segmentation for them, and they were like, "Yeah, we don't think that this is what it should look like." And I'm like,
This is then funny stuff that doesn't matter where you live in the world. People come to you and you know with the age of the PI, I want a 100x with a confocal.
Yep.
And you say, yeah, I know what you get.
oh gosh. Yeah, that actually explains it, actually.
And we have to talk money.
How often do you get the PI to back down, though, is the question. Sometimes.
Technically, I'm very good in confronting him with questions he couldn't answer any better. Because I say, okay, you are right when you have a physical amount of light, the 1.49 is the better objective than the 1.4. But when the light limit hits, it's not, because the 60 is
Just as much.
3 times brighter than the 100. Meaning, you get a better signal to noise and then the better resolution is 60.
Yeah.
No 100. Oh, since when?
Crazy. But also that's the benefit of like you existing in the imaging course. Like they have to find me. Like they have to like round around the university and be like, where is the person?
That's even what they teach in the visualization. Take your first 3 images from the control, take your 3 images from up, and then go to date.
Yeah.
It's like when I heard I'm done with imaging, it's like, no.
We're just starting.
This is not all this. You're not done with imaging. Not at all.
That's nice.
When I do like instrument readings too, I kind of try and explain, okay, what to think about when choosing an objective, like what is neutral dimension, like working distance and all that. But at the end of the day, I feel like when I ask them, okay, so what objective do you need? And people go with like, oh, I think the 20x will give me the most information that I need. That's like they don't know instruments or something like that. And then I keep telling, so before you do the analysis, take a few images, run it, come back.
I'm getting too old for this in the way of
Patience level.
yeah, it's not that's not true. But the German side now is decided to open control because when they come to me and say I want a 20x, that's a magnification. I want the resolution. You understand the concept of
they don't know that.
Yeah, I understand.
So hard.
But they have to go back and tell me what resolution is.
Yeah.
Because no, I understand. This is a magnification. I'm not asking for the magnification. What is it? I don't know. Then go somewhere and figure this out.
I will say though that just researchers depending on the internet to tell them what resolution is. Have you ever just Googled resolution? Okay, don't. It's not good. It's not great.
That's good for us.
It is great for us, but it's not great when you're in that situation. You're like, go figure it out.
No, but it's the same thing. Ask ChatGPT for fundamental processing. He learns what's out there. How often will you convert this to 8-bit? Because it's out there. Something like
well, that and image drain is a big problem. Right. It's out there. And so, it's going to be interesting. Okay, let me tell you something really interesting, though. In the last session of the class I was teaching, I threw in a session on using an LLM to write a Fiji macro. Probably something somebody would try if they were going to whatever. And at the beginning of class, I said, who has used an LLM to do any part of their analysis? I had one student of 20 raise their hand.
No, I have everyone.
I'm like, what is this? But they did they truly, I think, did not know. Like, they truly had not tried. Like, so we spent the whole rest of the class going through and writing PT macro. The point was, like, it's terrible. It gets you somewhere, but, you know, it's not great. That was the point. And I really, truly think that they were, like, lost. It never experienced it before. I was so surprised. I was literally blown away. Me too.
And so the last time I went in there was last Stanford, I just copied the metadata of the microscope into Chatty, and then I say, write me a method nature system. And he did. And then something like,
Was it good?
yeah.
Oh, wow.
It was too specific because there was stuff in there where say the temperature of the camera was -5.
Sure.
Because it was in the metadata.
Right.
And something like nobody would do this because they didn't expect people to
That's
read this.
really nice, though.
But it was better than 98% what I get from my users.
Absolutely, because they probably just say I used the 9 times.
Exactly.